We will just start our session on the topic foundations and deep excavation. So I am the session coordinator. So I hope all of you will be knowing the theme of our session, foundations and deep excavation. And I would like to introduce our distinguished chair, Professor C.N.V. Satyanarayana Reddy, and co-chair Sandeep sir for today's session. Now I will hand over the session to chairman and co-chair.
Good afternoon to all of you. So I'll briefly introduce myself before the session starts. I am Professor C.N.V. Satyanarayana Reddy, working as Professor and Head of Civil Engineering at Andhra University, College of Engineering, Visakhapatnam. So I have a teaching experience of 33 years, and I have published about 140 papers in reputed journals and reputed conference proceedings, and I have guided 17 PhD scholars successfully so far, and another 8 scholars are working under my guidance. So I am also serving on Executive Committee of Indian Geotechnical Society, and presently I am serving as Chairman of Indian Geotechnical Society, Visakhapatnam chapter. So I am confirmed I have been conferred with several awards considering my academic and research experience, like Engineer of the Year award from Government of AP in 2006, and also I am recipient of Best University Engineering Teacher Award in 2022 and AP Scientist Award in 2020. I am serving as a member of several technical committees, to name a few: H4 Committee of Indian Roads Congress, and serving as a member of Technical Committee on Scour and Erosion of International Society of Soil Mechanics and Geotechnical Engineering. So I feel extremely happy to be here to get associated with you all, to listen to your deliberations on the important topic, that is foundations and deep excavations. So as all of you know, with the present day requirement, we are going for high-rise structures, skyscrapers and all. So that needs a thorough investigation of soil and adopting suitable foundation to support heavy loads in the given subsoil conditions. Not only that, as you are planning high-rise buildings, to meet the requirement for parking, you are excavating deep below the ground surface to create cellar, subcellar, floors and all, right? So whenever you make such excavations, you need to adopt proper supporting systems. Otherwise, it will lead to instability and collapse of neighboring structures. So hope we will have useful deliberations from the others who have contributed papers for this theme. We have about 11 papers. So depending upon how many have loaded their papers, we will have the presentations. The presentation time is 9 minutes. So prior to presentation of papers by the others, there will be a thematic lecture that will be given by Dr. Sang Seom Jiang on the topic of pile raft foundation and soil structure interaction. So he'll be taking about 15 minutes. After that, contributed paper presentations will start. Now I invite co-chair to come on to the dais and introduce himself to the participants, please.
Renuka Consultants, Explorers and Designers Private Limited. We are in this positions for more than 25 plus years. We are leading this organization, providing end-to-end assessments in complete life cycle of the structures, starting from all geo parameters for the ground for major infra projects. We have been contributing to major projects, infra projects in Mumbai, starting from MTHL, Coastal Road, MCRP. We do have a booth, do visit us and understand more about us and engagements with us. So current topic about the deep foundations and their deep excavations. The challenges associated with them not only are limited to the reality segments, but also the infra segments and necessities for them. So of the total 11 presentations, we would be keen to listen to them. In the meanwhile, I invite thematic speaker, Mr. Sansong Jom, for his pile draft foundation and soil structure interaction session. Thank you, and I'm opening the session for the presentation. Thank you.
You briefly introduce yourself
Okay.
and then start your presentation.
Okay. Please open my slide. I am just Sang Som-jung, coming from South Korea. I'm still professor of Yonsei University, Seoul in Korea. In my case, I'm just most of the time staying in university. I have working on, especially on some deep foundations for the most of the time for the research and academic sectors. So today, I'm talking about some biological foundation and soil structure interactions. The topic is very boring topic, but still. In geotechnical engineering, I think we are so many soil structure interactions we can encounter in the engineering field. That's why I'm just focusing on most of the interactions, especially in pile-up foundations today. And then just my co-worker is Jinu Lee, is a master's student, he's standing, and okay. And making this project a successful success. No, no action. Okay, just introducing some of the deep foundation. Very just a fundamental concept of deep foundation. And then I'm moving into the pile-up foundation designing. Especially I'm developing some of the commercial code like mega piles in Korea and worldwide. I'm introducing, and then finally I can show a case study, especially on the pile-up foundation, and then conclusion. This is a very typical example cases you can encounter for the foundation problems. The left one is showing some kind of interactive problems, especially the coupling between the loft and soil. We call this interactive problems. However, on the right, just a figure showing non-interactive. You can imagine some of the rigid foundation or some of the flexible foundations, there is no interactions between the raft and the soil deformation is only controlled by the contact pressure. So we can define interactive and non-interactive. So in case of interactive, maybe we can imagine there's interactions between soil and foundations. So this is the figure showing some of the rigid foundation, showing this shallow one. For the left one is a rigid foundation showing. This morning, Dr. Mark Barlow is talking about some deep foundations for the laterally loading pile, for the flexible and rigid. Same as the shallow foundations, we have a rigid foundations, has some uniform settlement and uncoupled between the foundation and soil. However, in flexible foundation, maybe you can see there is a different contact pressures at each different locations. There is a maximum and minimum, and there is a different, some kind of non-uniform settlement and pressure we can expect. That's why we call this coupling between the foundation and soil. So focusing on the right flexible foundations, and then we can expand some concepts. Let's see, it's a typical just example, the foundations. You can see, to support some of some high-rise buildings on the left figure is standing on the shallow one, and then another in the middle, there is the group piling standing on the group, and the other right one is the pile raft. Depending on the foundation type, we can expect different load settlement behavior. Like on the right figure is showing the ladder. One is in between, the shallow one, and the blue is some kind of rigid pile groups. So depending on just the foundation type, we can expect different behavior of some kind of settlement. So we can count on some kind of settlement-based design. We can do more. We can do more economical designing. Why? Let's see. So in this kind of concept, I published some papers on this, especially in case of some soil structure interactions of bilateral foundation. Like in the bottom, just the journals, I just published some papers in each of them. So I can say, most of the engineers in these days, they are focusing on the capacity-based design. You can do everybody, but in case of settlement-based design, it's more better to ensure serviceability of the superstructures. So we can make a small diameter on some kind of friction piles compared to the large diameter and the bearing piles. So we can reduce all some kind of pile just dimensions based on settlement-based designing. So interactive analysis. Let's see, interaction between the superstructures and the substructures. There is in between, there is a raft. So you see here, this left figure is showing some kind of interactions between the structures and substructures, and then we can expect some stiffness values or some designing node in both of them, and then we can make some enlargement of this just the foundation part on the right figure on the flexible raft foundation, showing some kind of some relatively some kind of some deformations depending on the raft and the pile systems. And then we can say most of the raft is not rigid. It looks like some kind of deformed behavior, some kind of deformed, some kind of this kind of just deformations. I call this the flexible raft, most of them. So to make this kind of flexible raft, maybe we can make some members to count on this kind of flexibility of the raft. So in soil, you know everybody, the Winkler's foundation model, it looks like the upper one is showing. Due to some loading, only at that point there is a deflections. It's not a real case. Compared to the bottom one, is showing some kind of actual displacement profile of the most of the foundations. Like the bottom one is the real cases compared to the Winkler's just kind of theoretical, some kind of model. So in the analysis, to count on this kind of some flexibility and some kind of soil deflections, we can introduce some kind of some soil springs, like using enclosed foundation plus some kind of shear interactions called here. I used the Pasternak time model to count on some kind of membrane effect of the foundation level. So it's the key. And then probably this is a raft, and then depending on so many different loadings, like point distributed, some kind of bending moment applied on top of the raft, and then there is some resistance based on raft and the soil part. Count on this just sequence, and then next is some kind of piling. Why? It's a pile raft. So raft portion, we can count on some kind of flexibility in the analysis, also in the piling. It's very simple. In the intermediate, some theoretical point of view, it looks like a beam column analysis. It's a beam column, maybe. It's not very detailed analysis, but it's in between. Simple and very theoretical part in between is a kind of beam column. So you know well about some kind of a beam column for the axially, laterally, and some kind of torsion behavior of the single pile and group piles. And then we have a corresponding some kind of differential equations, like governing equations for the some kind of equations we can introduce, incorporate to make this kind of behavior. And then that's the key. It's a piling and then raft. There is interactions in between. In the interface, we call the pile head or some kind of raft. And so some kind of stiffness values like here. In the interface, there is some kind of variations of translation, some kind of bending moment, and then we can make some kind of a 6x6, some kind of coupled stiffness matrix to count on some kind of piling raft behavior. So this is a typical case of a 6x6, some soil stiffness values based on some axial lateral rotation and the coupling part, and then introduce this kind of stiffness values in the analysis. And then also you see here on the pile raft and just a kind of piling, it's not a linear just behavior. So it gives us some load settlement behavior. It looks like a nonlinear behavior. To capture this kind of nonlinear behavior, maybe you know it's mathematically there's kind of some iterations to make nonlinear, to capture the nonlinear behavior, some kind of load settlement behavior in the analysis. And then, just to make a long story too short, like this kind of pile raft, it's a flexibility. Also, we know we have some kind of beam column and some kind of soil springs all together to involve some kind of soil spring coupling effect. Also, this method is a kind of improved interactions of raft, soil, and pile systems. So it's a flow chart, but it's a simple to make a very complicated problem into some kind of a simple one based on some kind of stiffness just values for the raft, piling, and soil all together, making this kind of some stiffness value. Sorry. This is the circular one showing some kind of the combination of all the stiffness, contribution of all the stiffness based on some kind of piling, loft, soil, making this kind of a global stiffness matrix. It's a typical structural analysis. Maybe we know this kind of structural stiffness values we can count on in the analysis. And then finally, about 15 years ago, I proposed this kind of some analytical method to counter all kind of external loading on this loft based on the piling systems. And then we proposed this kind of analysis for the flexible loft foundation cases. So this is the kind of, I call this the mega. Why? Piling, just loft is very mega, means a big size, giving you flexibility of the loft. That's why called mega piling. And then making this kind of a commercial code, but the in-house code I made, and then it already is just done in the academic sector. So from now on, this is the case studies just we performed based on this kind of analysis. I'm not just a founder, because there are simple methods proposed by very well-known professors, Dr. Poulos and Landolf. They are doing so many simple and some complicated systems into these pile loft systems, but still I also made our own just code like here, and then compare our result with some field case studies. So in our university, we made some kind of some construction works for the engineering building. And then at the time, just in the section view, maybe we count on one pile groups to instrument and to measure some kind of some load sharing behavior of some just behavior. And then that's the typical plan view of the 5 different piles. And then we making instrumentations. So here, it's typical to measure the load transfer between from the top to the bottom, and then we can install some kind of strain gauges and some pressure cell there. Some of the kind of some instrumentations we performed, and to make a long story too short, as the one-story building going up to 10-story buildings, and then we can install some kind of loadings versus the corresponding settlement of the foundation level, and then compare this just measuring result with my just analytical result, like here. This is the the piling installed some strain gauges on the front and the back side, and then we can make some measurement, and then as the building story is increasing up to 10-story buildings, and then we can count on some kind of settlement behavior measured and then compared. Our prediction result is showing some kind of some dotted line is a kind of prediction by some mega piling code compared to some measuring some kind of, this is the one total compared to some piling. Depending on the piling and the total loading, we can compare our just calculation result with some kind of measured result, and then it's not exactly the same, but we can capture most of the behavior. It looks like the same behavior as the installation processing. And then another one is okay, I'm fine. There is a typically high-rise buildings is constructing in South Korea in the very just good the reconstruction just site, and then we have some kind of these systems already done in Pohang in the southern part of the Korean peninsula, and then our just result compared. And based on thoroughly detailed site investigation result we obtained, and then based on n value, some kind of strength values all together. And then finally, originally, our just construction company made some kind of just basic design, like original designing. And then, based on our analysis, we can reduce some of the number of piles and the length of piles based on the raft analysis. And then, this is the typical result of the comparison between the some kind of the square is our prediction result compared to the some of the other commercial code. Maybe you know some of them, FV multiplier, and looks like the same behavior we can capture based on our analysis. And then finally, based on some kind of this analysis, we can identify the settlement criteria. Also, we can identify these calculations. So most of them, we can capture most of behavior of the pile raft behavior based on our analysis. And then, tentatively, I can conclude the most important thing in the soil structure interaction is based on detailed site investigation. It's the number one. If we don't have some site detailed one, it's not easy to capture some of the results. So the conclusion one is the very important, most of them. And then our testing result is the raft pile flexibility and the soil pile nonlinearity. We can count on, and then the method can be done to capture most of the real behavior of the pile raft foundation. And finally, the pile raft foundation is the practical solution, my opinion, for the construction high-rise buildings, and is proved to be an economical alternative to conventional foundations. Okay. This is my presentation. Okay, thank you.
I guess there are no questions, so can we proceed? Nobody has raised hand or something like that.
So any questions from any of the participants?
Thanks for your good presentation. So my question is like, when in the combined pile raft foundation, when pile is located on weathered rocks, how it will increase the load sharing ratio to the raft? Yeah, when piles are resting on the weathered soils or weathered rock, how that component will increase, or how, it's like how much percentage of a raft load bearing capacity will get increased on that?
Most of the initial starting point is looks like about 20% or 25% is just resisted by the laughter. It's almost starting point in most cases. So the remaining 75 is created by the piling, and the other 25% is just created by the laughter. It's the initial point, and then making some kind of several iterations.
Yeah, yeah. Yeah, I got it. Yeah. Thank you.
Thank you very much for your presentation, sir. I would call upon next contributed presentations. Performance evaluation of combined pile draft foundation subject to combined VH loading. Aman Garg, Vishwas Savant and Siddharth Mandirath. We are running out of time and I would request to keep it short, a minimal time of 9 minutes. Thank you.
This one is correct, na? No, it's coming after.
A very good evening to everyone. My name is Aman Garg. I am here to present my work titled Performance Evaluation of Combined Pile Draft Foundation subjected to combined vertical and horizontal loading. These are the outlines of my presentation. As Professor told that the effectiveness of combined pile draft foundation for for supporting high-rise building and heavy structures. In combined pile raft foundation, both raft and piles contribute to support the coming loads. And as we know, every structures have only vertical loading. There can be simultaneous loading can occur due to wind load and seismic load and some eccentric load. So due to that, there can be existence of lateral loading. So it is very much needed to evaluate the performance of CPA, combined pile raft foundation, under combined loading. In my work, I have evaluated the performance of a CPRF model of 12 by 12 configured pile in a homogeneous sand, and I have developed vertical horizontal failure envelopes to get the insight of load interaction behavior and the effect of pile spacing and slenderness ratio has been investigated. These are the numerical models. On the left, we can see 3D discretized model, boundary conditions, and on the right side, we can see cross-section of combined pile of 12 by 12 groups in a homogeneous sand. Then in the study, I have modeled soil as a Mohr column in which the behavior linear, elastic, and perfectly plastic. Secondly, raft and piles are modeled as a volume element, material behavior as linear elastic material, and the interaction between pile soil and raft soil has been simulated using interface element, as we can see the modeling of piles in figure 3. Before conducting numerical study, numerical model has been validated through centrifuge experimental study conducted by Horikoshi et al. In which they have used 2 by 2 combined pile raft model in a homogeneous sand, and these table 1 shows the properties of the soil, raft and pile. This figure 4 shows the variation of load deformation curve. Left side shows the vertical load versus settlement, and the right side shows the horizontal load versus horizontal displacement. Red line shows the variation due from present study, and the dark black shows the experimental study. From the figures, we can see our present study results are in good agreement with the experimental one. For current study, 12 by 12 pile configured CPRF model having 80 meter wide square raft with 0.6 meter dia piles has been investigated, as we can see from figure 5. Also, parameter has pile cylinder ratio has been varied from 25 to 40, and pile spacing ratio effect has been investigated with variation 4 to 7. From the figure 6, we can see variation of vertical load carrying capacity with respect to pile spacing ratio for different L by D ratio. We can see from the figure, as spacing ratio increases, vertical loading carrying capacity increasing non-linearly. It is about increment of 7% for L by D 25. Similarly, if the increment when S by D is equal to 7, it is about 14% for L by D is equal to 40. So from this observation, we can see pile spacing have a more significant effect for a longer pile. Then similarly, horizontal load carrying capacity variation has been investigated for with the presence of vertical load or without the presence of vertical load. From the figure, we can see it's with the increment of S by D, horizontal load carrying capacity increases from up to 7 to 10%. Similarly, with L by D ratio, there is no significant impact, but in the presence of vertical load, there are around 12 to 11 to 16% increment in horizontal load capacity. Next, VH failure envelopes had been plotted for different L by D ratio and S by D. We can see from the figure that with increase in the vertical load to maximum vertical load carrying capacity, the ratio of horizontal load to vertical load increases, and it increases up to 0.75%, and after that there is not much increment from in this ratio. And similarly, the effect we can see with the increment of with increase in L by D ratio, there is a decrement in the horizontal load ratio of the horizontal load carrying capacity to vertical load carrying capacity. Similarly, with S by D increase in S by D, then there is a decrease horizontal load carrying capacity ratio. So these are the percentage of the decrement, and from the current study, following conclusion can be made that it is very much needed to evaluate the performance of CPRF under combined loading, because we can optimize the design of CPRF. Also, the impact of different pile spacing ratio and L by D ratio also should be investigated, because pile spacings have significant impact on both vertical loading and horizontal loading. But from current study, current model, L by D ratio effect is more on significant on vertical loading, not negligible effect on horizontal loading. Also, the study also established VH failure envelope for CPRF, revealing nonlinear interaction between vertical loading and horizontal with diminishing horizontal to vertical load ratio beyond 75%. This can offer insight for design applications. So these are the references. Thank you so much.
Any questions? One or two questions?
just the result you can expect. You can understand. So based on your analysis, maybe you are comparing your result with some result after that, vertical and horizontal, but initially your three-dimensional modeling has no validation, I think. How do you think about it? But there is a difference between volume and embedding file. So, yeah, in most of the filing, it's better using the volume, just the embedding file compared to the volume, giving you the real result. That's why I'm asking.
I have because volume element will have a more realistic behavior. It can provide more realistic results, so that I use volume element. Generally, we use embedded beam element when there are large group of files. So to make to get initial results, or so that massing not have no because volume element, if I use volume element, there will be effect of mass, because lot of massing will take time, computational effort in volume element. In embedded beam element, it will get, it's a line element. So some of the study use embedded beam element. So to get more realistic behavior, I have used volume element. But
I have one question. In the second slide, you had mentioned raft element to be modeled as an aluminum. What was its significance?
raft element as a volume element.
Aluminum.
In the experimental study, they have modeled raft as a aluminum element. That's why I have considered here as a aluminum.
Okay, thank you.
Just I have a question.
Yes.
So you have shown settlement of pile under vertical loading as 20% of pile layer.
Settlement of?
Even lateral deflection also,
Yes, sir.
you have considered to the extent of 20% of pile layer.
Yes, sir. I have considered.
No, consideration also should be right. What is practiced outside? What is the permissible settlement?
Permissible limit
for piles under vertical loading and lateral loading?
Working around 10%. 10% of the
lateral loading?
10% of
5 to 6 mm.
Oh,
1% of pile layer maximum you can say.
Okay.
If you see any code. Similarly, vertical settlement?
In case of combined pile raft foundation, around 100 to 125 mm. In case of high-rise building, we use. I have considered from that codal provision.
Actually, pile groups also hardly we go up to 40 mm. 25 mm is more preferable.
25 to 40.
So you have taken higher tolerable settlements and lateral deflections, and explained the behavior of your pile raft subjected to vertical and horizontal loading. You should do it corresponding to what is specified in IS code. Stick to that and try to revise your work. That will be better. No one will accept if we conducted a study wherein vertical settlements are allowed up to 20% of pile dia and lateral displacement equal to 20% of pile dia.
I have
imagine 600 mm dia pile. 20% of that is
120 mm.
Can you allow that much lateral displacement for a pile, even under pile raft?
That
model anything we say, it will give some output, but
yes.
we should think, right?
Yes, sir.
So refer to the existing codes and accordingly carry out the work. So anyway, it is a good attempt to understand the behavior of pile raft. Okay, then. Thank you.
Numerical investigations of cushion-dependent behavior of disconnected piles raft systems. S. Rahul, P. Haldar, B. Manna, and G.T. Sahu.
Good afternoon, everyone. I am Shruti Raut. I am PhD scholar from IIT Delhi. I am here to present our work on numerical investigation of the cushion-dependent behavior of disconnected pile raft system. This study is done under the guidance of my supervisors, Dr. Prasun Haldar, Professor Bappaditya Manna, and Professor J.T. Sahu. This will be the outline of my presentation. So traditionally, we know foundation designs are categorized into two types: shallow foundations and deep foundations. Pile raft foundations combines these two systems to ensure the more effectiveness and cost effectiveness. Despite having its advantages, there are some factors leading to pile raft instability, such as number of piles are more, majority of load is taken by the piles, then higher pile spacing, axial stress and bending moments at pile raft junctions. There is a chance of joint collapse at the junction. So, to avoid these challenges, Wong et al. Came up with an idea of disconnected pile raft system in early 2000, in which cushion layer is introduced between the raft and piles, so the joint is eliminated. So the issue of high axial stress and bending moment is avoided. This foundation system has been used in Rio Anti-Rio Bridge in Greece. In this study, we have varied these three key parameters, which is cushion thickness from H by D ratio of 1 to 5, then cushion stiffness ratio of 1, 3 and 6. Then I have varied pile spacing from 2D to 4D. On right hand side, we can see the modeling details for Yamuna sand, Badarpur sand and medium crushed gravel. I have used Moore column model, and pile raft is modeled with linear elastic. Then boundary sensitivity analysis was done, and for 6 by 6 meter raft, and from that we found that this 3.32B, after that the boundary effect diminishes. So based on that, the model dimensions were set as 20 meter by 20 meter by 20 meter. Then in this slide I have shown the sequence of analysis. In initial stage, bed soil was generated, then piles were installed, then cushion layer was placed above the bed soil, then raft was placed, then the load was applied, then the numerical calculations were done. So to ensure the correctness of the model, validation study was done on the 3x3 disconnected pile raft system of 3 meter raft having thickness of 1.5 meter. Table shows the material properties used, and on right hand side we can see that from load settlement curve, present analysis and FEM shows 0.46 meter of settlement, which is in close agreement with the Park et al. 2020, which shows 0.39 meter of settlement. Now moving ahead with the results and discussion. For the effect of cushion thickness, I have varied the H by D ratio from 1 to 5. All the settlements are calculated at this point A. Then these two non-dimensional parameters we have used, settlement efficiency and pile load proportion. From the load settlement curve, we can see that as the H by D is increasing, settlement is decreasing at particular load value. And from this bar chart, we can see pile load proportion is decreasing with increasing cushion thickness. Now, if we see the structural behavior of the central pile, from this first plot, we can see axial load versus the normalized pile depth. And for H by D ratios, we can see zone of maximum axial load in pile shaft moves downward as the thickness is increasing. Then next is unit skin friction plot, in which we can see that neutral axis shifts downward as the h by d increases. This can be explained through the last plot of pile soil relative displacement, in which we can see that soil displaces more than the pile in the shallower depth, which leads to the negative skin friction, and below that pile displaces more, which leads to the positive skin friction. Next is stress distribution plot. Here I have seen the stress below raft and below cushion. This solid below raft stress, which is not uniform and higher in magnitude, concentrated at the center. Then below cushion, if we see that with increasing the cushion thickness, stress is reducing and it is more uniform. This can be further seen by the contour plots of stress on pile head. Here also we can see that with increasing the cushion thickness, stress is reducing. Now moving ahead with the effect of cushion stiffness. Here I have varied the cushion stiffness ratio from 1, 3 and 6. From the load settlement curve, we can see that at particular load with stiffer cushion, settlement is reducing. Pile load proportion is also increasing from 27 to 47%. Then for the structural behavior of the central pile, zone of maximum axial load in the pile shaft moves upward as the stiffness is increasing. And from second unit skin friction plot, we can see neutral axis shifts upward as the stiffness ratio increases, and the same we can see in the inset plot of the pile soil relative displacement. Now for the stress distribution plot, we can see below raft stress is increasing with the stiffness ratio, but below the cushion stress is reducing as the stiffness is increasing. And this can be further seen from the contour plots, as we can see below raft with increasing the cushion stiffness, stress is increasing, but below cushion it is decreasing. Then going ahead with the pile spacing influence, I have varied the pile spacing from 2D to 4D. From load settlement curve, we can see that for unpiled raft, settlement is highest, but for all the DPR cases, settlement is less than that. But for 2D, we can see the difference, but for 3D and 4D, it's almost matching. And pile load proportion is around 35 to 38%. Then in structural behavior, we can see zone of maximum axial load of pile shaft moves downward as the S by D ratio we are increasing. Same can be seen from the unit skin friction. Then in pile soil relative displacement, soil is displacing more in the shallower depth than the pile, so it is leading to the negative skin friction at shallow depth and then positive skin friction. Then for the stress distribution plot, we can see for 2D, stress is, this is below cushion, and stress is around 125, and it is almost reducing by 25% when we are increasing the pile spacing to 3D, and there is minimum marginal change for the 4D spacing. This can be explained through the contour plots at pile heads. As we can see for 2D, the pressure bulbs are overlapping. Then for 3D, it is just touching the pressure bulbs of each piles. And then for 4D, they are separated. There is no overlap. So we can say that the 3D is the optimum spacing. Now based on this study, these are the conclusions I have drawn. Thicker cushions spread stresses more uniformly and reduce pile loads, but excessive thickness lowers the settlement efficiency. Then higher cushion stiffness improves the settlement control and pile engagement through the benefit becomes marginal beyond a certain stiffness. Then increasing spacing from 2D to 3D enhances load sharing and stress distribution, but wider spacing adds little improvement. Now we can see that at last why DPR is cost effective and economic design approach. In disconnected pile raft system, piles are disconnected from the raft and piles act as subsoil reinforcement, and it increases the overall stiffness of the system and reduces the settlement, and load is distributed between the piles and raft, and it not only improves the performance but also it is cost effective design as
1 minute more.
lower stresses and lower bending moment and lower axial stresses. So lower grade of concrete we can go and less number of piles we can use. So less than reinforcement bars are also required. So disconnected pile raft system is cost effective design approach. These are some of the references I have used, and thank you for your attention. If you have any doubt or you want to connect, this is my email ID. Thank you.
Any questions? Just one question we can have. Thank you. We can take it in next.
So you are disconnecting a raft
Yes.
from the piles and introducing a cushion,
Yes, sir.
right? So how does it behave when it is subjected to moments?
Sir, actually this
Because the stiffness of cushion material is going to be less
Yes, yes.
compared to raft or supporting underneath piles.
Yes, sir.
So how do you address that issue?
Sir, we are considering it as a raft foundation on the reinforced ground. Like piles, we are considering as a reinforcement and for the raft foundation.
More or less, you are laying raft on
Reinforced ground.
ground, right? That is introduced with some
With the
piles,
piles.
as reinforcement.
Yes, yes. Yes, sir.
Okay. So what is the cushion material?
Cushion is mainly helping in the redistribution of the load, sir.
Material. What type of material do you suggest?
Sand. Sand also we are using and medium crushed gravels.
Okay. What will be the ideal thickness?
Around 1 meter. We are having the cushion thickness also, like in the ratio of h by d. I have varied from 1 to 5 and diameter, like h by d ratio is 1 to 5. But around 1 meter generally is used.
So did you compare your results with the case where piles are connected to raft? Generally what people will adopt in the field?
Yes, sir. Yes, sir. I have done that also. Here I have not included that, but
What specific advantages you are getting by introducing cushion between piles and raft?
sir, in connected, if we consider the connected pile raft system and disconnected, in connected piles are taking majority of the load, and here we are. If in that case it is taking around 90% of load, but in disconnected it is coming down to only 30%. So the load on the piles will be less, so pile requirements will be less. We can go for higher spacing and number of piles will be less. So in that way it is cost effective approach, but we are suggesting this for the low to medium rise building, not for high rise building, because wind load effect and all will come. So that's it.
Whatever soil that is falling in between the piles will be subjected to higher stress.
Yes.
So there is a difference of stiffness between pile and intervening ground.
Sorry, sir.
When load is distributed uniformly underneath your cushion,
Yes.
right? Pile stiffness and whatever soil that is
Surrounding the pile.
right, there is a
Yes, yes, yes. There will be the settlement difference in the pile and the soil, which will lead to the negative skin. That's why in connected pile raft system, maximum load will come on the top of the pile. But here, as I have shown in the axial load plot, if you have seen, maximum load will not come at the pile head. It will come somewhat below depth.
Thank you.
Thank you, sir.
I call upon next speaker, Mr. Model load test on lateral resistance of soil cement composite pile. Testiro, Ninato, Shigai, Koga, Nova Q, Teachi. Try to wind up in 5 minutes.
I'm Naito, yes. Okay, good afternoon. I'm Tetsuo Naito. Thank you for your introduction. It is a great honor to be able to speak with you today. Today, let me share the model load test on lateral resistance of solid cement composite pile. Now, in urban areas with narrow space and low overhead clearance, several pile construction methods exist below these photos. But many problems remain in these methods, such as construction space or bearing capacity and settlement issues. And nowadays, noise and industry waste have also become important problems. So a new mechanical mixture ground improvement machine has been developed. First, this machine has higher drilling capability due to rotation mechanism and vibration mechanism. Second, this machine is very compact. Third, this machine reduces construction-generated soil. And to apply permanent foundation piles constructed by this machine, a soil cement composite pile has been developed. This construction method involves pre-mixing to the predicted bearing strata, followed by the installation of H-shaped steel as the core material that supports the structure. This pile consists of H-shaped steel and soil cement. In this pile, confined compression strength of the soil cement is from 500 to 1,000 kilonewton per meter squared. So the rigidity of pile is lower than steel pipe piles or precast piles. Therefore, lateral resistance characteristics and failure mechanism were unclear. In this research, to evaluate the lateral resistance characteristics of the soil cement composite pile quantitatively, model load tests were conducted in the gravitation field. Now, I'd like to explain model load test specification. In these experiments, 1/3 model piles of the standard full-scale soil cement manufactured. These full-scale piles were supported at the bases. Then, the model piles were manufactured by 1/3 size. The length of these piles are 1,000 millimeters. In some cases, the acrylic cylinder was set to simulate underground conditions. The loading was applied in the one direction, and loading position was set at the 150 millimeters above the soil cement. Lateral loading was applied by a loading jack, and actual load, in some cases, actual load of 30 kilonewton was applied by this lever block. Test parameter was a pile diameter, strength of soil cement, existence of restraint of pile body, loading direction, and existence of actual load. Now, I'd like to share the results from these tests. This graph indicates the lateral load on the vertical axis and the displacement on the horizontal axis. First, I'd like to show the effect of existence of the soil cement and its diameter. Regardless whether loaded in the strong or weak direction, the case with soil cement caused large lateral loads at the same displacement compared to the case with H-shaped steel without the soil cement. Next, let you see the effect of existence of restraint of the pile body. This restraint simulated underground condition by the acrylic cylinder, as I said earlier. For the cases with a pile diameter of 5 to 100 millimeters, no clear difference due to the restraint of the pile body was observed. However, in the cases with a pile diameter of 300 millimeters, the lateral resistance increased. To put it simply, soil cement diameter affected lateral resistance characteristics. Here you can see the effect of strength of soil cement. In the cases with a pile diameter of 200 millimeters, no difference due to the soil cement strength was observed. In contrast, for the case with the pile diameter of 5 to 300 millimeters, it was observed that the higher soil cement strength resulted in greater lateral resistance. So I can say soil cement diameter affected the lateral resistance characteristics. Finally, this slide shows the effect of applied axial load. When laterally loaded in the strong direction, it is confirmed that the cases with axial load shows larger resistance, lateral resistance than cases without axial load, regardless of pile diameter. On the other hand, when lateral loaded in the weak direction, it seems that the cases with the pile diameter of 300 millimeters, so increased lateral resistance due to the axial load compared to the cases with the diameter of 200 millimeters. So it can be said that soil cement diameter affects the lateral resistance characteristics. In the previous one-direction loading test, no clear failure of the pile body was observed. Therefore, after the one-direction loading, additional one-direction loading test with the pile head fixed was conducted. In these tests, fixing jig was set 100 millimeters below the soil cement. This is the observation result of the failure modes after additional tests. As you can see in this table, when loaded in the strength direction, diagonal cracks appeared on the front of H-shaped steel, that means the passive side, and the block was pushed forward. In addition, for the case with a pile diameter of 5 to 100 millimeters, only this crack was observed from behind the flange surface of the H-shaped steel, and this side block was pushed forward. When loaded was in weak direction, similarly, diagonal cracks also appeared on the passive side of H-shaped steel, and this side block was pushed forward. However, focusing on the pile diameter of 200 millimeters, horizontal cracks was observed all around on the horizontal side of the soil cement. These observations suggest that the failure mode differs depending on the pile diameter, and difference in failure modes affected the results of the one-direction loading test. Notably, regardless of the pile diameter, the elimination between
1 minute more.
Okay. Elimination between soil and H-shaped steel behind the flange by loading a strong direction, and triangular wedge-shaped crack appeared behind the H-shaped steel by loading in the weak direction. I'd like to summarize the main findings of this study and close my presentation. Thank you for your attention. And do you have any questions?
Any questions?
So when you study the lateral load capacity of soil cement composite pile,
Yes.
The main factor governing lateral load capacity will be the strength of soil cement, not the reinforcement, H-shaped steel, rolled steel section which you are keeping. It does not come into play, because we measure lateral load capacity corresponding to allowable deflection of 5 to 6 mm only. So within such a small deflection,
Yes.
the reinforcement action would not come into picture.
Yes.
Mainly lateral load capacity depends on the casing material, soil cement composite. What is the soil in which you have injected cement to form the soil cement composite around that reinforcement?
Your question means surrounding condition of soil cement composite pile.
Which soil? Is it a granular soil or Kozo soil or Kozo frictional soil?
In this research, we conducted in 1G test because due to size of pile, but we are planning to conduct a centrifuge model test.
Okay. Did you notice any change in lateral load capacity when loading direction is changed for H-shaped? Strong direction, weak direction.
Strong, weak. Yes. Sorry.
Did you notice any difference in lateral load capacity?
Yes, seismic loads act on the both weak direction and strong direction. So we design the both load, but sometimes if
maybe you have loaded up to failure without bothering about lateral permissible limits. That's why you are saying, right, in strong direction when you load, you are having higher load capacity and all. Actually, when you look at allowable lateral load deflection, you won't see any significant difference in lateral load capacities. Right? So try to look in this aspect also. So anyway, it is a good study, right?
Yes, later. Yes.
So many factors are there. Right, that too compared to your soil cement composite.
Yes.
Right, the tensile strength of your reinforcement is much higher. So under lateral loading, you cannot load up to the extent to which, right, the central reinforcement will be strained laterally. By that time, composite will fail. Okay.
Okay.
I would invite next speaker, Designing Against Failure, Early Lessons on Geotechnical and Construction Pitfalls by Govindraj and Madan Kumar Anam. Welcome. Due to paucity of time, would be grateful if you could expedite it. Thank you. 5 to 6 minutes.
So, very good afternoon. I'm Govind from Keller. The topic of my presentation is Designing Against Failure, Early Lessons on Geotechnical and Construction Pitfalls. Excavation failures are not just engineering errors, they are preventable disasters. So, you can see the one extract from the Syria C760. So the Syria is calling the embedded retaining walls as medium risky structures. That means category 2 structures. So it is not severely risky. But we can see a lot of excavation failures across the world. The left side, you can see the picture of one of the tallest residential towers in the world. This is Infinity Tower of Dubai, with a 27-meter excavation. So excavation started in 2006, but in 2007, when the excavation was completed, the pit failed. And you can see the top of the crane here. And in 2012, the project completed. So generally, projects in Dubai, they will finish it in 1 to 1.5 years. But this project took 6 years, which had so much cost impacts and time delays. So this is a classic example for the construction failure. Below you can see the Nicole Highway failure, which is an example of the design failure. So 9 out of the 10 failures are not happening because of the deficiencies in the state of art. They are happening because of the oversight. And on the right bottom, we can see the famous Dunning-Kruger chart, where it is actually relating our knowledge and our overconfidence. So if we are having less experience, we will be more confident generally. And if we are having very high experience, we will have so much questions and we will be less confident. You need a balanced approach. So this shows various type of embedded retaining walls, out of which the diaphragm wall is one of the best. Best in the sense it is having the less joints. But is it always like that? Now let us see one case study. Actually, this is an excavation pit. I just shown only one part of it. This is 19-meter excavation overseas. So the client had done similar pits in the past, very near to this. So soil condition is same, excavation depth is same. So they approached us, and originally they wanted 6-meter wide diaphragm walls. But when we looked around, we could see some 10-story building very near to this, around 10 meters away from the excavation pit. And this was supported on the deep piles. But one extended podium was there, which is very close to our pit, which is supported on the shallow piles. So the problem is that the moment you excavate a 6-meter trench, you are creating a zone of instability. So we can see the nearby piles in blue and red colors. And we made the calculations. We tried to make the calculations with the Plaxis 3D, and we could identify that the trench stability is around 1.17 if we are going with a 6-meter trench. And the nearby piles will settle something like 30 millimeter. So even though the diaphragm wall is one of the best solutions, we thought, okay, we will not go with a 6-meter diaphragm wall. So then we explored the possibility of a 2.5-meter D wall. So we had a better factor of safety of 1.38. The pile settlement went down to 9 mm. But finally, after all calculations and after thought process, we decided to go with 800 mm secant pile walls with a 640 mm center to center. By using this, we had a better factor of safety, and the settlement reduced to 6.4 mm. Now, let us see the second aspect, build-only retaining walls. So this is whenever a contractor comes to a build-only contract, we are in a dilemma. So the client, because client and consultant may be having experience in the nearby areas, and they might have designed for a lean system. As a build-only contractor, you are not supposed to make so many questions. And but at the same time, client will be having confidence because of the confirmation and information biases. So here you can see one pit in the Chennai with 12-meter excavations. If you just look very closely, it is actually not 12 meter. There are some deeper pile caps near to the D walls. So it is actually 14 meter. But for the client, it is 12-meter excavations. And they had done a similar pit in nearby, which actually performed very well. But when we were making calculations, we were getting high deflections and high bending moments. You can see the left plot, which is the monitoring data for the nearby plot. So this is not matching. And here, this clay, actually we have to do the trained and untrained analysis for any kind of retaining walls. Then we looked around what can be the causes. Then we identified that the water table is 8 meter below. Actual water table, when the pit was excavated, was around 8 meter, whereas during the soil investigation time, it was 4 meter. Also, it was excavated in a very short period. The excavation was completed in a very short period, and it essentially went into an untrained mode. But as a designer, can you consider it? Because the original water table was 4 meter, but in reality, when it was excavated, it is 8 meter. So as per BS 8002, we can see that whenever we design any kind of excavation pits, we need to consider the full amount of water pressure. We have to consider the failure of the dewatering systems. We have to consider the possible flooding situations. So here we can see, if we have shown the deepened pile caps near to the wall. If we had designed for the deepened pile caps, then deflection would have been, toe movements would have been higher. Also, if by mistake, if the operator excavate another half meter more, definitely you can see that the wall is going to collapse. So in almost all international codes, it's a must that you have to consider a half-meter additional excavation when you make a design. But Indian codes are actually silent on that particular aspect. Now, here you can see how the water table is going to kill us. The original water table was 4 meter as per the soil investigation. At the excavation time, somehow it was 8 meter because it was excavated in summer. But if the water would have increased to another 2 meter, and so the wall would have failed. So, as a conclusion, past success is not guarantee for a future, no guarantee for the future results. Whenever we are making a excavation pit design, we have to consider all the critical conditions like surcharges, additional excavations, water table increases, dewatering failures. So also, even though diaphragm wall is one of the best solutions across the world, it is not that we blindly go with a diaphragm wall. Maybe there will be case histories where there are nearby piles which can create a trouble for you at the longer run. So we may have to look at even the construction aspects when you are going with a diaphragm wall. That's all. Thanks.
Thank you for keeping it short and sweet. Any questions? Thank you.
Govindraj, nice presentation. Clearly highlighted, you can go just summarizing. You have clearly highlighted why failures occur in spite of adopting a suitable technique for soil retention deep excavations. So what are the various causes that may lead to failure? He has clearly explained. Hope all of you have got sufficient insight into that subject.
I call upon next presenter, Effect of Anisotropy on the Torsional Response of Pile Foundations by Vipin Kumar Gupta.
Good afternoon, everyone. So I am a faculty at IIT Kanpur. So I'll be talking about this particular topic, effect of anisotropy on the torsional response of pile foundations. So you can see from this particular figure that you have a pile embedded in a soil and it is subjected to torsional load. So how do anisotropy arise in geomaterials? So in the first figure you can see that you have a clay layer deposit, and when clay layer gets deposited, it is deposited in horizontal layers, and finally after consolidation, the material properties in the horizontal direction is different from the material properties in the vertical direction. Similar is for these sand deposits. The anisotropy in sand deposits arises particularly because of the particle shape and the sedimentation effect. So when the sand particles gets deposited, so the larger dimensions are along the horizontal directions. And because of that, the anisotropy arises in sand deposits as well. Then you have these rock deposits. So usually in rocks, what happens, they have bedding planes as well as fractures. And because of these reasons, you have anisotropy in rock deposits as well. For example, you can see an example of a particular rock which is gneiss rock, and they have horizontal bedding planes. And when you have these kinds of bedding planes, then you have anisotropy. So for all these kinds of geomaterial, you have a certain degree of anisotropy associated. So this kind of anisotropy is usually called the transverse anisotropy or cross anisotropy. So what is transverse anisotropy? Elastic properties in the horizontal and vertical direction are different. For transverse anisotropy, the properties in the horizontal direction is symmetrical about the vertical axis. That is, the horizontal plane has a plane of isotropy, and that's why it's called transverse anisotropy. Here are some examples where structures may be subjected to torsional loads. For example, you can see the example of offshore platform, oil and drilling rigs. You have offshore wind turbines, and then you have radar antennas. And obviously, most of these structures use piles as their foundation material. So what are the sources of torsional loads that you can have for these kinds of structures? So cyclones and impact forces from accidental ship collisions on offshore structures. For both these kinds of offshore structures, you can have cyclones or impact forces that might generate torsional loads. Wave and current action, that is always there. There could be torsional load because of machine vibrations. And for this particular case, the horizontal movement of this radar antenna can generate torsional load onto the pile foundations. So essentially, this particular presentation is on torsionally loaded piles embedded in anisotropic soil deposits. So I'm going to talk about a small analysis that we have developed and bring in some amount of results from it. So there are quite a few formulations available in the literature. So there is the simplified boundary element formulations, rigorous boundary element formulations, and then simplified analytical and numerical formulations, and rigorous analytical and numerical formulations. So what is this difference between simplified and rigorous formulations? Usually it is the 1 parameter and the 2 parameter model that they have. Most of these formulations that you have over here are either based on simplified theories or have complex mathematical schemes. What I am going to do is basically present to you a simple mathematical method which is rigorous as well as mathematically less complex. So you see that I have a pile embedded in a soil deposit. The soil deposit is homogeneous, but it is transversely isotropic. And you have two different values of shear modulus for the horizontal plane and for the vertical plane. So that is characterized by GSH and GSV. The pile is subjected to torsional load, and then these are the properties of the pile, and these are the dimensions of the pile that you see over here. And I'm using a polar coordinate system to develop the analysis. So I am assuming a soil displacement field in the very beginning, where in this particular soil displacement field, you see that phi p is the rotation of the pile, and phi is the soil displacement functions, along with other associated quantities. I use the elasticity theory to write down the stress-strain relationship in terms of this particular displacement field that I have. And this is the stress-strain relationship that you see. And you see that tau or theta, which is basically the shear stress in the horizontal plane, is associated with the shear modulus in the horizontal plane, whereas the shear stress in the vertical plane is associated with the shear stress in the shear modulus in the vertical plane. I apply the extended Hamilton's principle, in which K, pi, and WNC are essentially the kinetic energy of the pile, potential energy of the pile, and the work done by the non-conservative forces. And all these equations that you see over here essentially comprise of the potential and kinetic energy of the pile, potential and kinetic energy of the soil, and then you have the work done by the force applied.
1 minute, please.
Yeah. So we get differential equations. We get differential equations which we end up solving analytically. And then finally, we verify our analysis with existing analysis in the literature. You can see that I have the pile head stiffness versus the dimensionless frequency, and I end up getting a very excellent match. For this particular problem, the degree of anisotropy is 1, where delta S describes the degree of anisotropy. To find out the effect of anisotropy, you see that as the degree of anisotropy increases, the pile stiffness or the pile head stiffness also increases. This is the real part of the stiffness, and this is the imaginary part. The imaginary part does not get affected much, but you see that oscillations arise as the degree of anisotropy decreases. Similarly, the effect of anisotropy on the soil displacement field has also been investigated. And what I see is that as the degree of anisotropy decreases, the rate of displacement increases with radial distance, sorry. So here are some of the conclusions from the study. Present formulations produces excellent and accurate results. Degree of anisotropy substantially affect the prediction of pile head stiffness. Real part of pile head stiffness reduces with decrease in the degree of anisotropy. Imaginary part varies within a narrow band. Degree of oscillation increases with decrease in the degree of anisotropy. Rate of soil displacement function increases with decrease in the degree of anisotropy. So here are some conclusions from the study, from the analysis that we have found by running up a few results. So this is all from the presentation. Thank you. So if you have any questions, you can ask me.
It's a good study. You have given at the end general conclusions.
Yeah.
You could have given your study-specific conclusions.
Okay.
That is the only suggestion.
Yeah.
Any further questions? We can take up. Next one is study on loading rate effect on geomaterials for vertical bearing characteristics and evaluation of oil. Kyokoa, Kona, Koji, Watanabe, Suchi Suchum Lin, and Suchin Kamini.
Good afternoon, everyone. I'm Kyoko Kono from Aichi Institute of Technology, Japan. I'm in my second year of graduate school. I'll present on this topic. First, let me give you some background of this study. This picture indicates SLT. SLTs are highly reliable for evaluating vertical bearing characteristics, but they come with high cost and take construction time. Here's RLT. RLT, on the other hand, are simple to perform and have advantages in terms of both time and cost. However, there are still many unsolved aspects of the mechanism of dynamic effect. If RLT result can be accurately analyzed as static vertical bearing characteristics, more rational load tests can be performed. The final purpose of this study was to illustrating the mechanism of dynamic effect. In this presentation, in relation to the in situ and prototype behavior observed in full-scale test. Different loading rate traction compression tests were performed to confirm the rate effect observed in the element test behavior of geomaterials. This slide shows the test conditions. Test materials are Toyota sand and kaolin clay, and specimen size and diameter is 50 millimeters, height is 100 millimeters, and physical properties are shown in left tables. Here is the showing the condition for Toyota sand specimens we tested. Here, table. In our series, the relative density was set to 80%. This is because to simulate the behavior of ground at the pile tip. All the tests were conducted under saturated conditions. Series 1 and 2 were drain tests at confining pressure of 100 and 500 kilopascals, while Series 3 and 4 were undrained tests with the same pressure conditions. For kaolin clay, the consolidation stress was 500 kilopascals, and the confining pressure was 250 and 500 kilopascals. For Toria sand, we tested 7 loading rates from 0.0005 to 25 centimeters per sec. And for covering clay, 3 rate at 0.005, 0.5, and 25 centimeters per sec. This figure shows the triaxial apparatus system used in this study. For raw loading rate of 0.005 centimeters per sec and 0.005 centimeters per sec use an electric gear apparatus. For rate between 0.05 and 25 centimeters per sec, a hydraulic apparatus was used. These apparatus systems maintain a constant loading rate, so cancelling the effect of internal forces and allowing for the measurement of only rate effect. To confirm this, the acceleration was calculated by taking care second derivative of the measurement displacement. By multiplying this acceleration by the specimen mass, the internal force was confirmed, but it was a value infinity close to 0. On the vertical axis, each value measured moving on the test result of Toyota sand. These graphs plot loading rate on the horizontal axis and normalize each value on the vertical axis. On the vertical axis, each value measured at a given loading rate is normalized by the value at the lowest loading rate of 0.0005 centimeters per sec. First, look at the normalized failure strength. In Series 1, saturated sand under partly drained condition shows a sudden increase of the peak strength from 0.05 centimeters per sec. From the relationship between deviator stress and actual strain, the peak strength at a loading rate of 5 centimeters per sec approaches that under undrained conditions. In addition, the effect of loading rate on increase in stiffness was confirmed. This sudden increase in peak strength is mainly because the loading rate is faster than the rate of poor water pressure dissipation, and partly because the deformation mode changes. The loading rate effect of granular materials is said to be affected by these 3 factors. Although these limited tests don't allow us to draw general conclusions about each of the 3 aspects, we can talk about the overall influence of strain rate on strength and deformation in the next slide. Next, the internal friction angle at the maximum stress ratio was calculated. At a loading rate of 25 centimeters per sec, the normalized internal friction angle is about 1.25 times larger than the value from triaxial test conducted at the recommended strain rate of 0.0005 centimeters per sec. This graph plot deformation measures against the loading rate relationship. The deformation measures increase with higher loading rate. Specifically, it becomes about 2.0 times larger in Series 3. Even sand with high permeable, looking at the result for Toya sand, even this highly permeable sand shows increases in all the values because of the rate effect. Now let's look at the result for covering clay. Here is a graph showing how the normalized failure strength changes with loading rate. Regardless of the confining pressure, as the loading rate increases, the barriers get larger. At the loading rate of 25 centimeters per sec, the failure strength increased by about 30 to 45%. This graph shows the relationship between the normalized deformation measures and the loading rate. The barriers get larger at the loading rate larger too. At 25 centimeters per sec, the deformation measures increases by about 25 to 30%. This trend is similar no matter the consolidation condition, whether normally consolidated or over-consolidated. Here are the conclusion of this study. That's all for my presentation. Thank you for your attention.
Any questions? Next presentation is, thank you.
Thank you.
Static and rapid load test with various interpretation methods on steel pile in sandy ground. Ramakrishna Mandal, Sushira Kami, and Isaku Yamahato, and Tastumori Mastumuto.
Good afternoon, everyone. I am Ramakrishna Mandal from Jiban Sekenjo Company, Tokyo, Japan. I am going to give a presentation on a static and hybrid dynamic rapid load test on a steel piles in a sandy ground. The contents of my presentations are here. Introduction, a static load test. A static load test is the most reliable method for obtaining the load displacement reactions of a pile. However, SLT requires reaction force and loading devices which increase cost and test time. Hybrid dynamic ILT, which requires reaction system is not required. Load is applied by dropping a hammer onto the pile head through a soft cushions. Multiple blows are applied to the pile head, so it requires shorter time and lower cost. Now I am moving to the interpretation method. We have 4 interpretation methods. First one is ULPC, unloading point connection method. In this method, pile is assumed to be a rigid body in which a non-linear spring expresses the static resistance and linear dashport expresses the dynamic resistance. The pile having a mass yams and F rabbit and acceleration are measured. F rabbit is the sum of initial dynamic and static resistance, which is given in equation 1. R square is estimated using equation 2, and static resistance is estimated using equation 3. This figure represents the relationship between load displacement curve and static soil resistance and ULP resistance. In this, horizontal line is a pile head displacement and vertical line is a pile head load. In this, black line is a applied rapid force, blue line is a soil resistance, and this red point is a static soil resistance. At the maximum pile head displacement, when the velocity is 0, then that point is regarded as a static soil resistance, which is also given in equation 4. In the ULPC, in hybrid dynamic rapid load test, a multiple blows is applied to the pile head, and at the maximum pile head displacement, static load displacement is by connecting the static resistance, we can obtain the static load displacement curve. Now the next one is ULPC CM, unloading point connection invoking the case method. In this method, the pile is treated as an elastic bar in which a downward driving force and upward driving force is calculated by using equation 5 and 6. RT is the R square, which is estimated from equation 7. Now the third interpretation is alpha beta method. In this, equation 8 is the equation 8 is the modeling of a pile which is given by the Rudolph and Dick in 1992. And third is techniques to estimate the static soil resistance, which is given by Brown 2004. And equation 10 is just the extension of the equation 9. New proposed method, alpha beta method. In this method, generally in Japan, the load test is conducted by the static load test, in which the minimum velocity is 0. So the equation 10 can be modified as a
1 minute more, please. Conclude in 1 minute, please.
1 minute?
Yeah.
This is a new proposed method. At the F rapid max, the R square equation 11 can be written as equation 12. In this, the same thing is shown in the figure. This is a site condition profile of soil SPTN value and CPTQT together with the estimate test file is shown. The ground table is this is a test sequence specification of test file having a pile length of 11.8 meter and embedment length of 11 meter. This is the load test results using ELPC, CM and ELPC. This is IRT signal at a height of 0.83 meters. At the maximum pile head displacement, the velocity is 0, then a static soil resistance is obtained. This figure shows the relationship between F rapid, R soil, and static soil resistance using ELPC, and second one is using ELPC CM. The proposed range of alpha and beta, we use the alpha is equal to 0.1 and 0.2 because the site is sandy ground. These are IRT signals. In this, in alpha beta method, the R soil is estimated, obtained at the F rapid max. This is a relationship between F rapid, static soil resistance using alpha beta, and this is using alpha beta CM method. Now the load test results. Comparison of load test results curve obtained from
Can you please conclude it? Because we have another 2 more speakers lined up.
Just 1 minute. The static soil resistance curve from the ULPC slightly overestimate the SLT results. This is the red line. Green line is the static using alpha beta largely overestimate the SLT results, and blue line is using ULPC method matches the SLT results well, and the load displacement curve using alpha beta method using alpha is equal to 0.1 matches the SLT results the best. Now this one is the last one is the calculations. Thank you.
Thank you. I request question and answers to be taken later due to paucity of time. Thanks a lot. I call upon next speaker, for seismic lateral capacity analysis of skirted ring foundations in layered soil. Kaustubh Chatterjee, Puran, Pratik Goel and Sambit Pani. Okay, excavation induced deformation in adjacent pile foundations. Okay, with this again. Yeah, excavation induced deformations in adjacent pile foundation. Excavation induced deformations in adjacent pile foundations by R.B. Rao and S.S. Kandolkar.
Hello.
Request to keep it to 5 minutes as the time we have already overshot. Thank you.
Hello, I'm Radha Rao from Goa College of Engineering. This is the content of my presentation. The aim was to understand the impact of deep excavation on adjacent pile foundations. Objectives was to understand settlements, lateral displacements, stress redistributions. This was the literature review that helped me in my research. To name a few, and there were many more, but the methodology consists of soil properties. We have done the depth of excavations, varied it from shallow to deep foundations, 12, 24, and 36. Varied the distance from the old structure to the new excavation pit from 3, 5, and 8 meters. The pile diameter also is varied. We have considered 1 meter and 1 meter 1.5 dia piles. And to study displacement in soil, pile cap deflections, behavior of single pile, and pile group behavior. These are the properties that we considered for our study. The saturated unit weight considered is 17 kilonewton per meter cube. Young's modulus, 10,000 kilonewton per meter square. Pile cap design, it's 256 meters square with a depth of 40 centimeters. Young's modulus, 3 into 10 raised to 7 kilonewton per meter square. Pile, we designed a 4x4 pile group consisting of 16 piles, and each pile was designed to take a safe static load of 3,000 kilonewton. On the left-hand side, the sketch that you see shows deep excavations. L is the distance between the old existing structure and the deep excavation, new excavation that we have undertaken. Numerical analysis, we monitor displacements and stresses. Coming to results and discussions, as we moved towards the excavated side, we saw significant increase in displacements, that was settlement as well as lateral displacement. In this slide, the figures show how as the excavation, depth of excavation increases, the pile cap rotation is observed. Single pile behavior also was analyzed. So this slide, the pile which was at closest proximity to the excavation pit shows how the behavior is observed in the single individual pile. The distance to depth ratio less than 0.25 is very crucial. In this graph, again, we have come to an observation that distance to depth ratio less than 0.25, the lateral displacements have significantly increased. The depth to length of pile, which is kept constant at 25 meters, the ratio 0.5 to 1 is the transition zone where the bending moment is observed is maximum. To understand the pile, which pile behaves better, we analyzed 1 meter dia piles as well as 1.5 meter dia piles, and we have come to the observation that stiffer piles show improved resistance, that is 1 meter dia pile are more susceptible as compared to 1.5 meter dia piles. There is lots happening in this slide. If you see, at 4 meter excavation depth, the vectors are moving downwards, that is the load transfer is happening along the shaft to the tip of the pile. The other slides at 12 meter excavation depth, there are stress bulbs are getting truncated, there is soil collapse that is observed, and due to loss of soil confinement, the piles lose their frictional resistance and lateral stability, which causes increased bending moments and bending and tilting in the piles. This table is to simplify our results. Coming to the conclusions, higher L by D ratio, that is the distance to depth ratio, ensures safety. Distance to depth ratio less than 0.25 is critical. Higher distance to depth ratio ensures safety, and numerical analysis are performed. The effect on pile group behavior is seen that adjacent excavations alter soil pressure distribution, affecting the axial capacity. Critical threshold depth is that the distance to depth ratio is less than 0.25, highlights the need for strict excavation control. Thank you.
Thank you very much, Madam, for the presentation. Any questions anyone has? I request Chairman to conclude the session.
Thank you. Nice presentation. So I'll briefly summarize. So first I would like to thank the thematic lecturer, Dr. Sang Seom Jeong from Yansi University for his excellent work on pile draft foundation, dealing soil structure interaction in a detailed manner by replacing soil with elastic springs underneath the raft as well as surrounding the piles. So such an analysis is very much required to precisely estimate particularly the serviceability benefits which we derive for pile draft foundation. So on behalf of the organizing committee of Geotech Asia, I thank him for presenting his excellent work here for the benefit of delegates who attended this session. So coming to the contributed papers, befitting the theme, foundations and deep excavations, we have papers addressing the various issues related to pile draft foundation, and most of the papers discussed on pile foundation, response of pile under torsional loading, behavior of piles under horizontal and lateral loading. And we have been exposed to new concept of disconnecting a pile draft system, introducing a cushion. So it is something different from what we really see in respect of a pile draft foundation. And we had papers on model tests assessing lateral resistance of soil cement composite pile. And we have an interesting presentation from Keller explaining the various causes that lead to failure of deep excavation supports in spite of adopting a suitable methodology. We had one more paper on response of steel pipe piles in sandy ground from static and rapid load testing. And finally, we had a presentation on excavation-induced deformations in adjacent pile foundations, particularly with respect to clayey soil. The others have dealt the effect of distance to depth ratio, right, on neighboring pile foundation. So clearly they have brought out that large diameter piles are less affected, and piles with diameter 1 meter are susceptible to settlements due to excavations, and clearly they have brought out, right, if L by D ratio is less than 0.25, it is going to cause significant settlement and all. So good thing. So the session is complete, and I hope all the participants have enjoyed the presentations. I congratulate all the others for their excellent works and submitting their results for this prestigious International Geotech Asia Conference. On behalf of the organizers, on behalf of myself and my co-chair, Sandeep Deshpande, Engineer Sandeep Deshpande, I thank you all for participating in this session. So finally, I thank the organizers for giving us this opportunity to handle the session and interact with you all. Thank you.
Thank you very much. As a token of appreciation, I request Professor Savaikar to I request Professor Sang Sam Jang to receive a small token of appreciation from, you can read, yeah. And request Professor Savaikar to give a memento to chair of the session. Yeah, this is your packet. Yeah, thank you. Thank you, Professor Satyanarayana Reddy, for conducting the session successfully. And to Sandeep Deshpande, co-chair of the session.
They want one photo.
Yeah. You bata diye. No, you just tell them that session is over and they remove this. Abajay, you come here.
So we are winding up the session. You
Yeah.
can please come for the photo session.
No, we need to tell them outside. You come out. No photo, nothing. They remove the partition. Now again, once again, the full hall. They remove the partition.